Hello, everyone, again. My name is Ross Signal. I'm the Director of Product Management at Dranitz. I'm joined here in the room today with two of our system support engineers. Those of you who are Dranitz customers have certainly worked with these folks before. I have Ken DeMario and Thurman Bridgers, who are certainly product experts on our product. They're going to help with today's presentation. Today's presentation will be part of our power monitoring seminar series, which we conduct around the country. We do these half-day seminars, and in the COVID era, we won't be doing those for the foreseeable months. So what we decided to do is bring those to you virtually, and we're going to provide 5 power monitoring seminars and modules, which is basically taking our normal seminar series and dividing it into 5 what I'll call digestible chunks. And this is the first of that. Module 1 is titled Introduction to Power Monitoring, and that's what we're going to be reviewing here today. So what's our agenda? Again, we have Ken and Thurman here to help out. We will be addressing your questions throughout the presentation today. Just note, we're not going to use audio. We certainly have too many people to let everyone use audio today to ask questions. We're going to be using the chat capability of Zoom here today. So if you go to your toolbar for Zoom, and it may be off your screen, but maybe hit that more button if you need it, and find the chat button or chat menu pull down, and chat up to everyone your question, please. And you can certainly do that during the presentation. Ken and Thurman will help me during that, and we'll pause when appropriate and answer your questions as we're doing the presentation, but certainly at the end, we're going to address all of your questions in the Zoom chat box over here. Feel free to ask questions about anything that we're discussing here for our seminar presentation, anything Dranitz, or any other questions that we may be able to help you with new products, with existing products, or anything that we can be of assistance with. So our next training is going to be on August 9th. That will be what PQView can do for you. That's actually hosted by our sister company, Electric Tech Concepts. So if you go to the same page that you registered for this web meeting on our website, under our products and services, you will find a separate registration button for that meeting. So if you're interested in attending, feel free to register. That'll bump you over to the Electric Tech website, which will have a registration form, and you'll get a bounce back on that form with the link information in a very similar way that you got for this web meeting. So to get started here, again, this is Introduction to Power Monitoring. Again, we've broken our web meetings, our power quality seminars and power monitoring seminars into these chunks. The first one is the basics of power monitoring. So we're going to talk about what is electrical power monitoring. There are some questions in regards to that because monitoring is a very generic term. We're going to talk about how we're measuring, what tools that we're using to measure. And then we're going to start focus on what we're measuring. Are we measuring power? Are we measuring power quality? Are we doing both? How are we wiring our products? So we're going to give you some rules of thumb on how to wire your products into the circuit, which are very important. One of the reasons why the gentlemen are in the room with me here today is they deal with our customers a lot. And unfortunately, some people make mistakes and errors on wiring their products. So we want to give you the ability to do it right the first time. And it is focused on our Dranitz products, of course, but these principles apply to most products out in the field. So these are some tips to help you get it right the first time so you don't waste a week, a month, or whatever it could be on your on your survey and have some issues. And we're going to wrap up this section and talk about transducer considerations. And what we mean by those are PTs and CTs. We take a lot of them for granted, but the right choice of those PTs and CTs are very important to the success of your energy survey and or your power quality survey. They're very important. So again, chat up your questions. We are monitoring chat right now, and feel free to do that. And today's session will be recorded, and sometime later in the week, it'll be posted on our website. So a little review about Dranitz. I apologize if this is redundant for those of you who attended our last web meeting, but we are located in Edison, New Jersey. You can see here's Edison. It's a stone's throw away from New York City. So in normal times, those who are visiting New York or in the New Jersey, or what we call the tri-state area, we always welcome you to visit our factory. And we hope once this COVID thing dies down, we can welcome you again. We're in a very nice part of the country. So what is the Dranitz product and service portfolio? So we focus on portable three-phase power quality demand and energy instruments, and also three-phase portable energy-only instruments. We also make permanently installed versions of all those instruments. In fact, that was the topic of last week's web meeting, where we focused on our fixed products, but also introduced some new products in that product portfolio. And we're going to elaborate on what the difference between these two types of products are in a couple slides. Of course, in today's world, you have to make good software, so we have analysis and reporting and system software for each of those two product categories. Specifically for our portable, our Transducer software, which is world-renowned, and we've got thousands and thousands of copies out there. And for our permanent products, we have our PQView DE and our PQView software. That comes to us from our sister company, Electrotech, who's hosting that web meeting a week from today on the 19th. Some of you may not know we are the U.S. master distributor of Gauss and Metrowatt products. That's where ownership lies with Dranitz. They are the manufacturer of precision multimeters, testers, electrical safety, insulation, installation, and other types of testers, including light meters and transducers and sensors. So they are based in Europe. We are the US and North American and South American distributor of their products. And on the next slide, I believe you'll see a picture of some of those products. We do pride ourselves in the ability to support our customers. We do offer free technical support. The gentlemen in the room here are happy to help you, as I am and everyone else is, with any questions that you have about your products, both before the sale and afterwards. We want you to be happy with them. So as an extension of that, we provide remote and in better times, on-site product training and commissioning. These are paid for services. Well, we will focus on your application, work with you and your team to help you folks install the products correctly, configure them correctly, and then train you and your team on how to use the information and use the software that's appropriate for that product. So feel free to contact us if you have any questions about that. Please visit Dranitz.com, recently updated last year, and it's not only a library of information on our products, but it's also a library of educational information on the industry, of course, application and tech tips on our product, but also on the power monitoring industry, the standards. Again, our recorded webcasts are hosted there, and this is the same website that you registered for this presentation on. So just one point of note, we are located, as I mentioned, in Edison, New Jersey. Everything designed by Dranitz in this building is manufactured by Dranitz in this building. So we're proud to say made in the USA. And we have a large facility. First floor is manufacturing. Second floor is basically everything else. So just to put a visual on the products that we're referring to here, and then we'll get started. Again, we have portable three-phase power quality demand and energy instruments, and our latest product family is the HDPQ Plus series, which you can see here, and it's SP equivalent. These are portable instruments. And we have our fixed systems. Fixed systems we spoke about at our last meeting, and we have a variety of fixed system meters, from advanced power quality demand and energy meters to kind of middle of the road capabilities, very good power quality meters, but with strong energy capabilities. And that's these meters over here, as well as energy only meters. These are the new AM series meters that we introduced at last week's presentation. Each, as I mentioned before, has its accompanying software. With the portable, we have our Transducer software that's loved by many of our customers, and we have thousands of copies. And for the systems, we have PQView DE and PQView. Related software to each other. They come from the same base, but they're intended for different applications. So I mentioned earlier that we do distribute Gauss and Metrowatt products, and you can see some of their products here, from multimeters to safety testers to light meters and other types of products. So feel free to reach out to us directly, your local Dranitz representative, our regional managers, or any of our distributors throughout the world if you do have any questions about these products. So without further ado, let's get started. And again, this module is titled Introduction to Power Monitoring. So we're going to start off and kind of lay some basic terms here and make sure that we're all on the same playing field about really what is electrical power measurement and monitoring. Different people have different understanding of what it is. So let's just go down to the basics and how we term it. And really, you can look at this. The real answer is it depends. and it can actually mean different things to different people with different applications. So we're going to basically describe what the difference is in our world here. Measuring typically means real-time and instantaneous readings. So if you consider a multimeter just taking a reading, or a panel meter, you take a reading, your recording of that is writing it down. The meter is not doing recording for you. Where we consider monitoring, where that instrument, that meter, that panel meter has memory in it. And within the capabilities of that tool, it is recording those parameters over time, and it's storing those. And it's in today's world, that's like a DVR for your power monitoring. You get to go back and see what happens from the time you started monitoring till the time you stopped, or the current time here. So again, the difference is monitoring means that memory is involved in recording things over time. Metering is real time. You see something flash up. If you didn't write it down or remember it, it's gone, and the next update will happen. So that's really what the difference is. So when you break it down, what are the capabilities that you get with these different sorts of applications? So for measuring, that is really instantaneous readings. So again, the meter displays something, it goes away and displays the next reading. So for our purposes in electrical power monitoring, we're talking about spot checks of voltage and or current. Excuse me. So consider a multimeter. Yes, you can measure the voltage. Many times these are single channel devices. Then you can measure the current together. If you have something that has two channels, you can get voltage and current at the same time, but you're not recording this information over time. So it's just a spot check. And if you are doing voltage and current at the same time, those meters may provide computation of basic parameters such as watts, VA, bars, power factor, and things like that. So maybe this is a panel meter doing that for you, whether it be an older style analog meter or a more modern style digital meter with an LED or an LCD readout. Again, these are real-time updates, and they come and they go. The difference again is monitoring is those same tools have a form of memory in them. Again, various tools have different capabilities to them, but on an energy perspective, the recording of that information over time. So you can record electrical energy and consumption. That's the accumulation, that's integration over time of those parameters. And these are what our energy meters are doing. You know, for billing or energy assessments or power surveys and things like that. And the objective here is how much energy you're using or power you're using, what's the cost of it, where and when are you using this. So you're recording this information over time, primarily for demand and energy and costing applications. And that's for electrical energy in a power survey. When you use those similar tools and you have a power quality capable instrument, well, it's taking that same voltage and that same current, but it's looking at it a little bit differently. Think of it through a different filtered lenses. So you're not looking at accumulation and how much, but you're buying that instrument because you want voltage quality. You're looking for changes in that voltage and or current that can affect your processes, affect your quality of supply and whatever your operation does. So some of the more common things we're looking for are sags, swells, transients. We're looking for current changes, which are measured in a very similar way as voltage. Harmonics, distortion in the waveform we're looking at for voltage and current. But really the application is we're looking for the compatibility of the power source to the load. So you're concerned about possibly your susceptibility, your uptime, and maybe the economic effects of changes in the power, okay? And your application may include one or more of the above. It could be energy, it could be power quality, it could be both of them at the same time. So let's expand upon that just a little bit. If I can change my slide. There we go. So what's the difference between energy and power quality measuring and monitoring? Again, we're using the term monitoring from this point on. So our instrumentation has memory. Whether we're talking about energy, we're talking about power quality, those tools are recording this information over time. The time is the duration of your survey. Could be temporary or even a fixed meter, and we'll get to that in a second. So for the sake of this web meeting here today, we're going to use a generic term, power monitoring, because a lot of the application and rules of thumb apply to both power quality and energy. But they are different tools at their heart. So it's important that we understand what the difference between an energy meter is and what the difference between a power quality meter is that could also have energy capability. So their measurement requirements overlap, but they have different resolutions and accuracy needs. So when you look at energy, we're typically looking at parameters that are measured in seconds. Yes, you can measure, microwatt hours, but you could also measure megawatt or kilowatt hours. That's more of an appropriate measurement for energy. Okay, so high accuracy is usually needed, especially when you're doing something for revenue or billing and you have to meet ANSI or IEC revenue and billing standards. High accuracy is certainly important. Think of that revenue meter on the side of your business or your house. You want that to be accurate, and these are potentially certified meters. Not all the applications are, but really it's accuracy is the important thing. Where power quality, typically a power quality event is measured in microseconds or just a few milliseconds. So you can see the difference in resolution here, where energy is focused on seconds and accumulating information. One cycle and beyond, many cycles, where power quality is focused on AC cycles and subcycles. And again, here in the United States, one cycle is about 16 milliseconds, where in Europe and other parts of the world, it's 20 milliseconds. So we're talking that period of time and even shorter for certain types of power quality events. So really high accuracy is important. We all want accurate measurements, but it's not the overriding requirement, okay? You're really on a power quality survey, the difference between a 0.5% and a 1% accurate meter probably isn't going to buy you that much, that big of a difference. However, some of the international standards, such as IEC 61000-4-30, will require you to have a more accurate power meter. So, but also note that many of today's power quality instruments, including most of those from Dranitz, do have revenue level accuracy. So they're very good power quality meters, but they also can measure energy very accurately. So really, PQ instruments can often be used for energy surveys, but not vice versa. So why don't we pause a second and do a little poll here, and let's get an idea of what you folks are using. So if you guys can answer this poll here, do you use energy monitoring? Do you use PQ monitoring, or both? So if you guys can please just answer the question here, and we'll give it a couple seconds to look at the results. Okay, we'll give it another couple seconds here, and you guys can see the results right here. So most of you folks are interested in either PQ monitoring only or both demand and energy, not interested in energy only. So that's very interesting. We always like to see how our customers wish to apply the instruments. So thank you so much. I'm going to end the polling here. We'll have one more poll as we go along. Okay, so we'll just share the results here, and you can see there are your results. Okay, so about 53% of you had applications for both, 43% are PQ only, and only 4% of you who polled or answered the poll have an interest in energy monitoring. So thank you very much. I appreciate that. Okay, so let's continue. Okay, so how are we making these measurements? This is important. This goes to what type of tools that we're using. And as Kenneth Thurman here in the room will attest, our objective here from a support standpoint, and of course sales, is to make sure that you're using the right tool for the job. And we're not trying to upsell you necessarily on buying something you don't need, but we have a lot of customers who call our technical support. They've done surveys, and then you realize that, oh, they didn't use the right product. And so we want to make sure that you understand not only the capabilities of the tools, but there's also various categories of tools. And one of them is a portable instrument versus a fixed instrument in their application. So there's some differences here. So we'll start with portable. Portable, usually reactive approaches. So there's a problem that occurred, and you're quite frankly, a problem occurred, you're connecting an instrument, you're monitoring, and now you're waiting for it to happen again. So you're using your system as an alarm and as a beta test to see if you can capture the problem now. And if it is a power problem, your tool will capture it, and then you can go with that information and provide some sort of resolution to that problem. So usually it's single or just a few meters. They're typically handheld devices, really portable. We mean can be easily carried around and quickly connected and disconnected to your circuit, and of course safely done. Wiring connections are typically temporary, banana jacks, flex or clamp CTs, something like that. However, there is a trend for very strong communications. If you look at our HDPQ Plus line and our SP line from HDPQ, it has very strong room of communication. So You don't have to be in front of the meter or the instrument while you're collecting data. You can go about your business and remotely connect to it from wherever you happen to be, on your local network, on the internet, on a VPN, whatever it may take. So those are characteristics of fixed products as well. The last differentiator is desktop application software is typically used. In our case, that's our Transducer 7 software. Very powerful software, but it's PC-based software that is desktop used, opposed to a permanent and fixed application, which may have server-based software, and we're going to get onto that right now. So when you look and compare and contrast a permanent or fixed installation, as its name implies, these are permanently installed. The instrumentation or meters are there for the life of the facility. So what that allows you to do is be proactive in your measurement. So you can see problems before they turn into failures. You can see proactively from an energy standpoint, look at your trends of demand and energy and utilization, compare that to your utility bill, just to see if you're maybe hitting some demand limits or power factor issues or whatever that may add to surcharges or additional charges for you. From a power quality perspective, you can see power quality issues in your system that may not have affected you yet, but you could have a looming failure as a result of that. Sag, swells, transients, harmonics, or other issues that maybe not have caused failures today, but you need to look in to improve your uptime and prevent those failures for tomorrow. So usually these are systems with multiple meters, energy, power quality, both capabilities. Again, they're fixed installed. So they're panel mount, they're rack mount, they're wall mount. You screw these things into a panel and you screw the voltage and current connections in. So they're meant to be there throughout the life of the facility. Oftentimes you're connecting to PTs and other CTs for your measurements, okay? So strong communications are extremely important in these applications. So these are going to be installed at your service entrance, in a utility substation, in a UPS cabinet, a PDU, any sort of application, and you're going to be communicating with these instruments remotely. How do you do that? It's with server software, and that's where our PQView and our PQView DE software comes in. We're not going to elaborate on this too much. That was last week's presentation, but this is software that automatically communicates with these devices, downloads all the data, puts it in the database, and makes it readily accessible to you, in our case, via just a web browser, a multi-user access via a web browser. All right, so that's kind of the differences between portable and permanent. So what are the benefits of power monitoring? And everyone likes that little emoji on the bottom there. But really the primary benefit is problem avoidance and prevention. We have many case studies that have shown that proactive power monitoring can increase your reliability and prevent failures from occurring because you see problems before they result in failures and downside. I'll give you a real example without citing names. It's a large government organization that we work with, and they use a particular brand of UPSs, and they know that as these UPSs have aged, that they have transient problems on their output. They have these filter capacitors, and they know that when those transients start to occur, those filter capacitors are starting to fail. So they notice that on our systems, and then they proactively schedule downtime for those UPS modules in a redundant system, so they can take them offline proactively and correct that problem, because they know that should they let it go, that module is going to fail at any time randomly in the future. They don't want that to happen. They want to keep their reliability up and going. Okay, so that's just one good example. So the second bullet here is knowledge of your facility. If you don't monitor it, you don't measure it, you can't monitor it. All right, you don't understand what's going on. And this is from an energy perspective, as we mentioned before, being proactive about your utilization. Maybe you've done everything you can to improve your energy efficiency. You've gone to energy efficient lighting, variable frequency motors, whatever may be appropriate for you. But these are things you need to manage over time as well, because what you do today can be undone tomorrow as your facility evolves and other changes are made. So you want to be proactive and stay on top of these things from energy, but also from a power quality perspective that we spoke about. And the last one here, it helps you react quickly to problems that occur. So on a power quality basis, think of a mission critical environment where all of a sudden a server goes down and a major part of your facility or your services aren't operating anymore because you had a failure in your services. You can't, that service isn't working anymore. That server has failed. Well, is it a power problem? Is it not a power problem? Is it a communications problem? Is it a server problem? Well, information from these systems help you determine that. So in this case, maybe you're looking at the output of a UPS system. An IT person comes up and says, hey, we just had a rack of servers go down. We think we had a power problem. Well, you can go to your power monitoring system from Dranitz and say, oh, yes, you did have a power problem, and give them specifics. Or also conversely, no, you did not have a power problem. Maybe there was an issue with the hardware, the communication, something other than power. And we do know, as facility people and people in the power industry, fingers point to power first. And then it's up to you as the manager of those facilities, or a contractor or someone servicing that facility, to prove or disprove that it was a power problem. Systems like this give you the tools to do that. So these are the major benefits of doing this, certainly on a proactive basis. The alternative would be a reactive basis. You go and take one of our HDPQ pluses, you connect it to that same circuit, you hope the problem happens again, so now you can capture it or not, and then prove or disprove power. So this is the benefit of being proactive versus reactive. So how do we make these measurements? How do we do this? All right, and there's many tools available to us in the power monitoring industry, all the way from just basic multimeters through power analyzers. These are energy meters and data loggers, traditionally without power quality capabilities. Then we go into power quality instruments, whether it be portable or fixed, and again, usually certainly from Dranitz. They also have energy and power logging capabilities and other tools. Some of our customers use fault recorders, spectrum analyzers, oscilloscopes, and different things like that. So let's put up our last poll for today, and let's find out what you folks use here. So let's see if we can get our next question on there. And how do I go to my next question? End polling. Let's go to our next poll. I apologize. So what type of metering do you use? We mentioned kind of 4 categories here, 3 categories. So if you can please answer the questions here. Do you use a multimeter, power analyzer logger, power quality analyzer, all of the above, or maybe something else? This is a multiple choice question, so you should be able to check multiple things at one time. So thank you. I see the answers coming in. And by the way, there's no prize at the end of this, so sorry about that. So let's just wait a couple seconds. All right, I think we'll just give it another couple seconds. I still see some answers. I see people changing their answers. Okay, so let's end the polling and let's go share these results. So what do we have here? So most of you folks are interested in power quality instrumentation. About 20% are interested in power analyzers or loggers. A lot of us use multimeters. We all know that. We have that at home and also at our places of work. All the above is pretty significant. Okay, most of you guys use all the above, or at least a third of you guys, a little more than a third. And other. If you guys who use other, just please chat us up. I'm just interested to see what you folks use. So if you could just send a chat and let us know. So, okay, thank you. That was very interesting. We always like to get that feedback. So what we're going to proceed with right now, we're going to break these down, and we're going to talk about these individually and look at the pros and cons and some of the things that you should be interested in doing that. So going bottom up, we're going to start with multimeters. As we said before, we all know how powerful they are. They're extremely useful tools. However, they're not the most useful tools in this sort of application. They're single phase. They're sort of basic tools. They're good for what you can use them for. But you need to, if you are going to use a multimeter, just make sure that you use a true RMS multimeter. Some of the lower end multimeters, to save cost, the manufacturers use an averaging technique, and that sort of falls apart when we talk about harmonics and distortion on your voltage and current. So the recommendation is to use a true RMS meter, okay, and spend a little bit. Most meters have that today, all except for all but the least expensive of them. And a good example of that is I actually saw a case study one time. I can't share it because I didn't have permission to use it, where these 2 clamp-on ammeters were used from the same manufacturer. However, one was a low-end one, and these were monitoring the input or an output of a breaker panel. The low-end one was an averaging meter. The more elaborate one was a true RMS clamp-on meter, and they looked the same. and they were both measuring the current, and they had wildly different results because it was a highly distorted environment. So the true RMS meter was much more accurate in that. So again, rule of thumb, you want to make sure you use a true RMS meter. And if you're interested on the bottom, maybe if you can't sleep tonight, you can read this 3 times in your head and it'll put you to sleep. But this is the formula for an RMS calculation that most of the instrumentation uses. So then we kind of proceed up in that value chain or that capability chain, and we talk about power analyzers. Again, we're not talking power quality capable instrumentation here, but we're talking about meters, data loggers that focus on power flow. So you can have portable instrumentation such as our EP1 or other types of loggers, and fixed instruments. This is that new AM series that we introduced last week, the AM 1000, 2000, and 3000. So again, these are usually either portable and handheld or panel mounted for fixed installations. But again, be very careful about the capabilities because they vary by manufacturer. And one of the messages that we want to get across here in this section is make sure you look at your requirements and compare them to the specifications of these meters to make sure that they're going to do what you want to do. And a key thing is if you're interested in check metering or anything, checking a billing meter or anything related to revenue, you want to make sure you have the accuracy of these meters. So maybe the lower end meters won't work right for you. And you also have the transducer considerations that we'll speak about in a couple slides. So just keep that in your thought process. And again, differences are packaging, user interface, the amount of memory. Those are very application specific. So take a close look, make sure your tool is going to meet your needs. Now, when we talk about power quality instrumentation, we're going up a little bit in cost, not as much as it used to be these days. It's changed a lot. The power quality instrumentation is much, much more affordable than what it was even a couple of years ago. But the focus is on power quality, but they do have typically energy monitoring capabilities, certainly what you see here from the Dranitz portfolio. So again, you have the choice between fixed and portable. You can see our HDPQ Plus here, which is our latest line for portables, and a smattering of fixed meters that we have. This is from our 61000 family, HDPQ data node, and our PQ3K and 5K products. So again, the differences in your application and the packaging. Are you going to carry this around? Are you going to permanently fix it? That'll help you guide you towards one of these 2 different product categories that we covered before. But again, look at the capabilities of your products and see what's important for your application. A good standard to look for is IEC 61000-4-30, being Class A Edition 3. That's a topic of I believe that will be our 3rd web meeting when we talk about power quality capabilities. That's a very, very important thing for a modern power quality meter, is to have those capabilities. All of these are compliant with that standard, which all but this meter over here from the 61000 supports the latest revision. All these are the latest revision, edition 3 of that standard. That basically says you're buying your product from a reputable manufacturer that has recurring and repeatable results. That's what that standard's dictating to you. So again, a topic for another conversation. But again, make sure the capabilities of your tools are appropriate for the application that you have. However, when you look at it, when you look at just a block diagram, excuse me, of any monitoring device, any power monitoring device, and I do apologize, this CPU section looks like a floppy disk. That's not really what it was intended to do. The good news, my daughter took a computer history class in high school and knew what that looked like. So made me feel very, very old at that point. But it's not meant to have a floppy disk. We certainly have electronic memory today. But here's basically a flow diagram of a modern data acquisition device and certainly a modern power meter, where you have analog inputs and the analog to digital conversion process. This is extremely important. This is what defines the accuracy and the resolution and many of the measurement specifications of your instrument. So we take this analog signal, we convert it to digital by a process called sampling that we're going to talk about on the next slide. And that's about as in-depth as we're going to get. And we want to make sure we share that with you because it helps differentiate appropriate meters from maybe meters that may not be appropriate. And everything goes to a computer. It is analyzed by the computer, and then of course you may or may not have a user interface, an LCD panel, or maybe there's very strong communications with your instrument or both. And that's how we see the results of these instruments, okay? The building blocks are different, but pay attention to the specifications, certainly on the measurement specifications and memory specifications of your instruments. So sometimes you get what you pay for, even though prices have come down, make sure they meet your application. However, one of the biggest specifications before we move on here is the digitization and sampling. And the way digitization works is, and you can see by this kind of roller coaster image here, is this is an AC sine wave. So imagine that continuing along. Digitization is the instrument takes a measurement, and then X number, in this case, microseconds later, takes another measurement. So the rule of thumb is, to a certain extent, the more you digitize, the better your digitization, which is the more samples per cycle, or the higher frequency you're sampling each cycle, the better resolution that you have. And what that means is, if I take a sample here on this first point, I take a sample here on that second point, microseconds or maybe even longer later, I have no information in the middle. So your instrument is blind at that particular period of time. And there's a compromise between adequate sampling and oversampling and sampling too high, just because data files get big and memory doesn't last as long. It takes longer to communicate, different things like that. Okay, so just to put some numbers to it, back many years ago, 32 samples per cycle was common. So that's 520 microseconds in between these two samples. All right, that's a lot of dead time. So we kind of fast forward to modern times, and as we go through here, you can see as we double the sample rate, we're halving the time in between those samples. So there's an inversely proportional relationship there. So we double the sampling to 64 samples per cycle, we half the time in between these samples. 520 is now 260 microseconds. So where are we today? Most instrumentation, certainly the instrumentation from Dranitz that measures power quality, are in this range right over here. 512 samples per cycle. That means your resolution, or your dead time here, your time between samples, is 32 microseconds. So if I want to measure transients, I can measure transients in theory down to about 32 microseconds. That's quite good by today's standards. We do have products that digitize all the way up to 1 megahertz. That would be our HDPQ Plus Explorer, or HDPQ Explorer Plus instrument, and the Explorer SP. That's meant for more advanced applications, but nothing's going to go past that instrument. It digitizes to a microsecond. So really, this 512 samples per cycle, just kind of a rule of thumb, will get you maybe 75, 80, 85% of all power quality problems, where the Explorer level product in our product line will get you virtually all of the rest of the power quality problems. Okay, so again, you don't want to sample too high. A lot of the metering out there samples at a very high rate. However, you have to be careful, and you have to look at your specs very, very closely. When we talk from Dranitz, 512 samples per cycle, that means each channel is sampled at that rate. So most of our products are 8-channel instruments, 4 voltage, 4 current. Each of them is sampled at 512 samples per cycle. Other instrumentation may say, like as an example, it digitizes at 1,024 samples per cycle. However, that may be for 1 channel. So if you have 2 channels, that's 512 samples per cycle. 8 channels, that's 128 samples per cycle, okay, on 4 voltage and 4 current. So just pay attention, just buyer beware, just pay attention to those sorts of specifications, because there's some gotchas there. Okay, so what are we measuring? We're going to talk about wiring here and some rules of thumb as we get into the last 15 minutes or so of our presentation today. So what are we measuring? Well, we're in the electrical power distribution world here. So typically you're measuring 3-phase, and that's 3-phase Y, 3-phase delta, split phase, and single phase applications, okay? Most of the time with products in our category, although it's applicable to all of these, we're talking 3-phase delta, 3-phase Y. So as the gentleman in the room here, Kenneth Thurman, would attest, you need proper wiring configurations. This is a perfect example of garbage in equals garbage out. If you don't connect it properly, you could waste that 7-day or 30-day survey and just get no useful information. So we're going to give you some tips on how to properly connect your Dranitz instrument, which if you don't use Dranitz, we want you to use Dranitz, of course, but if you don't, you can apply some of these rules to what you use. So first we're going to start with something called Blondell's theorem, and it's one of the basic rules of thumb in our industry, and it was a long time ago where Andre Blondel, and you could read down at the bottom, back in 1893, it's quite some time ago, certainly before our smartphones here, he came up with a rule of thumb or a theorem that says if you want to monitor N electrical conductors for power quality was not a concern back in the 1800s, or in fact most of the 1900s for that matter. But if you want to monitor the power consumption in N wires, you need N-1 watt meters to do that. So that's a basic rule of thumb, that as we go through a single phase, a split phase, a three-phase Y, and then a three-phase delta, we're going to use that same rule of thumb. This rule of thumb applies to all energy monitoring capabilities or energy meters out there. It applies to most of the wiring configurations for power quality as well, but we're going to point out some differences here for a delta application. Again, so I'm continuing our rules of thumb. So here we have a typical single phase circuit, and so you need to measure voltage, you need to measure current. As we said before, current is usually measured using CTs and CTs of various types, and this is a clamp CT. Each CT, no matter what type, has some sort of arrow, and that's meant to be the direction of current flow. And that is from source to load is the convention. So that arrow should be pointing towards the load as you clamp it or clip it around that conductor. Well, we need to measure voltage. Voltage is the difference between 2 points. That is traditionally the line reference to the neutral. You'll see that for most of the applications. And we're not going to spend any time on this D or this fourth channel, but from a power quality perspective, this is neutral to ground monitoring. So you see D plus is neutral and then D minus is to the ground. So if you follow Blondell's theorem, how many wires do we have here? 2. How many watt meters do we need to measure this 2-wire circuit? 1. So that's Blondell's theorem. To have 1 watt meter, you need 1 CT, 1 current measurement, okay? No matter what you do, you need 1 current measurement. I apologize, I lost my mouse here. So one way to look at it is if I have 2 wires, I need 1 watt meter, I need 1 CT to measure that. So how do I get these things connected properly? And as the gentleman in the room to attest, you need your voltage and current to be connected properly. And the one thing to note on a single phase circuit with a power factor of 1, okay, so the voltage and current are in phase. If you look at the bottom, you'll see this. It's actually on screen on all of our HDPQ Plus and other family products. You can look at the difference between the angle of the voltage and the angle of the current. So with no power factor, they ride right on top of each other. They cross 0 at the same time. So the reason why we're giving you this, if you see the phase relationship between voltage and current being 0, you know you're connected properly, or being something with a reasonable power factor. As an example, if I would turn the CT and connect it wrong and that arrow is pointing towards the source, I would see the current 180 degrees out and pointing to the left here and not the right. So these are gotchas as you connect your instrumentation. And again, our HDPQ family will show you right on screen your scope, your phaser. In fact, it'll tell you whether it thinks it's connected improperly as you proceed in your setup. You want to make sure this is right, because it's hard to undo this stuff later if you walk away for 30 days and then call Ken or Thurman and say, hey, my data isn't right, what do I do? We can't undo a measurement of the instrument. Our Transducer software can reverse the CT, but any measurements previously making, we can't undo that for you, okay? So spend a couple minutes and make sure it's done right. That's the rule of thumb. So split phase, again, we just kick it up 1 notch here. So from a Blondell theorem perspective, how many wires do we have? We have 3. How many watt meters do we need? 2. How many CTs do we need? 2. Which direction of the arrow is the arrow? Pointed from source to load, so to the right in this diagram, okay? So the difference is we have 2 CTs. Each CT, the A phase CT is clipped around the A phase, the B phase CT around the B, and we're referencing neutral for all of the applications here. So we're measuring A to neutral for the A phase, B to neutral for the B phase. Again, here's our neutral to ground, which we're not going to spend much time on. So that phase relationship thing is exactly the same we spoke about for single phase, except the B phase is 180 degrees out from the A phase. All right, for those of us in the United States, we know the split phase wiring. Internationally, It's not very common outside of the United States, or I should say 60 hertz systems. Maybe that's more appropriate. Like Europe and Asia, you will not see this particular wiring configuration, but certainly the US and North America and other 60 hertz parts of the world, you will see this. Okay? So same situation, but you want to make sure that your B is clipped around B, your A is clipped around A. If you switch these, you're going to have your current 180 degrees out. But you can think how complicated that could be. So if I took B, clipped it on A, which is the wrong phase, but also pointed it to the left, it may look right, but it's on the wrong phase and you have it inverted. So think of the errors that can possibly be made. We want you to catch these things before you start your survey. So we recommend that you look at your scope and your phasers and you use the information from an HDPQ should you be using it to get this right. So now we kick it up one more notch. We're looking at a 3-phase 4-wire Y. Okay, and by the way, what I've spoken about are the proper connections for energy and power quality for single phase, split phase, and also for 3-phase Y. So going back to Blondell, we have 4 wires. We need N-1 watt meters, so we need 3 watt meters, which means 3 CTs. The difference between split phase and 3-phase Y is now we have 3 phases. Each are separated by 120 degrees. So here's the wiring difference between them, okay? So you can see A, B, C, this is the rotation. When you look at the traditional rotation of any phaser or vector that we talk about in our industry, the rule of thumb is just look at my cursor here. I'm gonna leave my cursor here. Rotate that vector counterclockwise. And I'm sorry, the cursor disappeared. So you could see A would come through that first, then B, and then C. It's a counterclockwise rotation. So that's how you would compare when you see A and A voltage and A current, you could see their relationship and see if you're wired correctly. So, but you can see we're measuring A to neutral, B to neutral, and C to neutral, and C, B, and A phases are clipped on their respective CTs. But look at this phase relationship here. You want to make sure and get assurance that you are actually clipped on the right current or clipped on the right phases, but also that your voltage is correct. So you want to verify that. So the most confusing one is a 3-wire delta. All right, this can be confusing, and one of the reasons it's confusing is because we're measuring phase voltage because we can't get a voltage measurement in the phase of a motor. So we can't get the line voltage in here. So we're measuring phase voltage. So we're measuring A to B, B to C, and then C to A are the measurements. So on the A phase, B is the reference. On the B phase, C is the reference. And on the C phaser channel, A is the reference, okay? But we're measuring line current. So that's a big difference. And we're gonna talk about that in our next slide, okay? And this is also where it differs between an energy survey and a power quality survey, okay? And I'm gonna actually skip a slide to point that out. So if we look at Blondell's theorem. So Blondell's theorem says I have 3 wires, I need 2 watt meters to make that measurement. And most of the, in fact, probably all the fixed panel meters to measure energy do a 2 watt meter method, which is what it's called. It's perfectly fine for energy measurements, but it's less than optimal for a power quality measurement. And that's why if you look at the Dranitz instrumentation, we have both a 3-phase 2-wire delta, which is to the right here, and a 3-phase 3-wire delta, which is to the left here. And what's the difference? So that to save the cost of a CT and potentially a PT, there's that 2-wire configuration. And what that means, and this is the Blondell-like method or configuration, where you take one of your phases. Let's call it the C phase here. It could also be the B phase. It's kind of arbitrary. Well, I'm measuring the voltage referenced A to C and B to C. I'm measuring the line current in A, and in this case, the line current in B. All right, and the meter will add up the total energy perfectly fine. That's the Blondell theorem method. The problem is from a power quality perspective, I'm not distributing my power A to C. I happen to be distributing my power B to C, but the meter has no C to A reference. So as a rule of thumb, when you connect a power quality meter, you want your meter wired in the same way as the critical loads that you're evaluating. So in a delta circuit, you have an AB phase, a BC phase, and a CA phase. You want your meter wired in and measuring those exactly so the meter sees what your load is seeing, and that's important. So you do not have that here in this particular application. So if we go up to the top, we have the three-phase, three-wire delta, which is appropriate for both power quality and energy. So I have 3 wires, but I'm going to do a 3-watt meter method on that. And what that means is that my voltage is connected A to B, my B to C, and C to A, and I'm measuring current on all 3 phases here. So of course my energy will be measured correctly, but my power quality meter is measuring the AB, BC, and CA phase. So in this case, it is seeing exactly what your loads are seeing and your power system is seeing. So from a power quality perspective, it has the opportunity to see exactly what's critical to you. All right. So the bottom one is for energy only and to save the cost and the wiring of that extra phase. This is appropriate for power monitoring, power quality monitoring rather. Okay. And the choice is yours in our instrumentation. Just be aware that an instrument connected this way basically cannot pick up all of the power quality issues. You have to be aware of that. Okay, so we have a question, and from Patrick, when measuring on a Delta 480 system, is there any benefit to connect the D voltage channel that's to ground? Well, that is actually, there's no benefit in your primary phases, Patrick. However, the one thing you need to be aware of, if I go back a slide here, or 2 slides rather, this is a 3-phase Y situation. Now, I have 2 choices when I'm connecting my instrument to this. I can connect it phase to neutral, or I connect it phase to phase, okay? So there is a neutral here, and the way we explain this to our users is the recommendation is you have a choice, all things being equal, do it phase to neutral. It's simpler, okay? However, if most of your loads are connected phase to phase, we would recommend to connect your instrument phase to phase. So Patrick, in your application, since there is a neutral here, even though all your power parameters may be phase to phase, if this is the case, you can still do neutral to ground to look at neutral issues, which may still be an issue on your system. So hopefully that was clear. If not, chat up another question and we'll be happy to answer it. Okay, last issue with delta and more delta confusion is the fact, just notice we're looking at the phase voltage and the line current. So when we talk about single phase, split phase, and Y, everything lines up. In other words, our voltage and current lines up. So if I have an ideal power factor of 1, they cross 0 at the same time. So visually they look good. In a delta circuit, we're measuring the phase voltage and the line current. The physics of that is that it's off by 30 degrees, just by the nature that we're looking phase voltage and line current. We can't control that. There's nothing, that's not a Dranitz issue, it's just the physics. So what that means is that the voltage and the current are off by 30 degrees. Perfectly fine, all the power will be added up and measured properly, but when you look at each individual phase, the power numbers aren't very meaningful to us. So individual phase numbers look off because of that difference in angle, but the total power will be measured fine. But that does cause confusion on a lot of our customers' part if they don't understand that. And I see Ken nodding his head here. Even to this day, we receive a heck of a lot of phone calls and emails about that very topic. So, okay, last section in this module here, our transducer consideration. So you can see what we're trying to do is prepare you before we go into our next sessions, and before we end today, we'll describe what they are, what those coming modules are, those remaining 4 modules of this seminar. We want to make sure that you choose the right instrumentation for the job. We want to make sure you wire your instrument in correctly. We want to make sure that your transducers are done correctly. So really the whole moral here is you're only as good as the weakest link in your chain, and not having the appropriate instrumentation could be a weak link. Not wiring it incorrectly or having wire mistakes could be a weak link, but also the improper application of transducers, which are PTs and CTs, could be an issue as well. So we want to make sure that we help you with that. And in fact, these are a lot of the tech support questions that we get. So when you look in Wikipedia and you look for what a transducer is, so in our world, just to describe it, a transducer helps you take something that is not directly measurable by our instrument and converts it into a signal, a voltage or a current that is directly measurable by our instruments. So from a voltage perspective, that may be a PT or a voltage divider. Like as an example, our HDPQ family and a lot of our products can go up to 1,000 volts, AC or DC. So that's a direct connection to the terminals of the instrument. If you're measuring a 13 kV circuit or anything above that, you need a PT or a voltage divider to divide that higher voltage down to something that's measurable by the instrument. Same thing for a CT. You're not going to wire 1,000 amps into one of our products. That's a big safety issue. So you use CTs that take that 1,000 amps and maybe have a 5 amp secondary or another thing to go measure that by the instrument. So you can understand what the difference in voltage and current transducers are. So, but we need to be careful when we choose these things, and we also need to be careful not to use them when they're not appropriate for your application. And Stacy, we have another question for you. We'll get to that in a few minutes here. At latest, we'll address that to the end. Thank you. So on for a voltage transducer, and you can see this is a single phase PT on the right. So direct connection, our recommendation is to use that in most low voltage applications within the voltage range of the instrument. And what I mean is don't unnecessarily use PTs, because PTs can act like a filter on your system. They're band limited, okay? So they can reduce the opportunity for transients and the bandwidth for harmonics. So if you can directly connect your instrument to your bus, if you're under 1,000 volts with our HDPQ and many of our instruments, do that. That's much more appropriate. However, if you need PTs and CTs, just note, or the PTs, that they may be band limited for your application. So many applications are using that, down to a 480 volt application, and many of the fixed metering applications would require the use of a PT. So the most common type is a PT, which is a voltage divider or a transformer divider. So there's a primary ratio, a secondary ratio. The instrument is measuring the secondary of that. When you set up the instrument, you enter a multiplication factor, so all the metering looks like it's on the primary side. So CTs, again, in our world, you're typically not looking at a direct current measurement. So you're not, except if it's under 5 amps in some of our permanent instruments, you're not wiring a current directly through our instruments like you would a low current application in a multimeter. So usually on our portable applications, you're taking one of our clamp and flex CTs and connecting it directly to the bus, or clipping it around the bus, or you're using a low current CT and maybe clipping on the secondary of a fixed CT, maybe a 5 amp secondary, okay? Just note that CTs fall into 2 broad categories. Those with a voltage output, maybe 1.5 volts, 3 volts, or 1/3 of a volt, okay? I apologize, that should be a decimal point there. Those are typically used in a portable application. The clamp-on type CTs or temporary CTs usually fall into that. And then there's another category that has a current output, usually 5 amp, typically fixed applications use that, okay? Just make sure you use only compatible CTs and check with the manufacturers. From Adranet's perspective, anything that you purchase with our products are, of course, fully compatible with our products, okay? That's an important thing. So when you look at the portable CTs, they fall into generally 2 categories. One is rigid or clamp CTs, as you see here. They do have a voltage output, and certainly the voltage output of our CTs are compatible with the current inputs, which are voltage on the CT. So our current inputs on our portable products actually measure voltage, and that's that low voltage, okay? These are very common for portable applications. So you have the clip CTs and the flexible CTs. These are by far the most common type that we sell. I would say roughly about 2/3 of our customers are buying these flex CTs. They will add clamp CTs, but they start with the flex CTs because, as its name implies, they're more flexible in probably 2 or 3 ways. The obvious one is the CT itself. This, if I can get my mouse back here, this disconnects at this black connector, opens up, and you can wrap it around your conductor, whether it be a wire bundle, a single wire, a bus bar, whatever may be appropriate. So you can bend it. It's flexible. It's physically flexible. Where these rigid CTs, you have to have the space. When you squeeze that clamp, it needs to be able to fit in that space, and you can't fit a bigger wire through that than what will fit with that clamp closing. So the flex CTs are more flexible physically in how they can be applied, but they're more flexible. They can service a wider range of current. So ours come with a switch setting for a 30 amp range, a 300 amp range, or a 3000 amp range, and we also have 6,000 amp versions of that as well. But they're also available in various circumferences or lengths. The most common size is a 24-inch 3,000 amp CT. By far is the most common size. So we have them in 36 or 48 inches. 48 is so long it's almost like a jump rope, but it's used for a lot of applications. So these are the differences, but note that there's a voltage output. In our case, it's a 1.5 volt output with a nice connector that plugs right into our meters. So in a fixed application, the most common type is either a solid core CT or a split core type CT. Usually they have a 5 amp secondary, and we measure that output. That 5 amp secondary, excuse me, is wired into the fixed instruments, and we're actually measuring that 5 amp secondary. You enter scaling factors or ratios into the instrument that makes it look like you're measuring that 1,000 amps and multiplies those values back up. So a solid core CT is less expensive, but you need to break your wire or your bus to fit into this. A split core CT is more expensive than the solid core CT. Solid core is the least expensive because in this case, there's a clips on the side. So you undo these clips, it pops off the top, you clip it around your wire or your bus, and you clip it back together, okay? In concept, they work the exact same way. You enter the ratio into your meter, and you're doing that. If you have a portable application and you have these fixed CTs, usually you take these wires, you clip one of our smaller CTs on that secondary. In our example, it's our TR2510B CT that we clipped onto there. So the meter is measuring the secondary, the instrument is measuring the secondary of that fixed installed CT. So as we wrap up in the next slide or two, you have to be very careful and make sure that the appropriate safety ratings are applied. And this is when you're actually looking at a voltage safety rating for a current transducer. And what I mean is when you look at the voltage safety rating on the CT, it's going to say 600 volts or 1,000 volts or even something less, depending upon where you get it from. Like as an example, our clamp CTs are rated for 600 volts. Our flex CTs are rated for 1,000 volts. So even though they're not measuring voltage, that's the safety rating of that wire or that bus, or the voltage going through that wire or that bus as you apply these transducers. So as an example, if I have a 13 kV application, it's not appropriate and it's not safe to take our flex CTs and put it around there. So, or our clamps, even though they may be within the current range of the measuring of that transducer, they don't meet the safety requirements of that. So be very careful. Okay, so some considerations when you're choosing these transducers, these PTs or CTs. So make sure the current or the voltage has the output that's compatible with the measurement instrument, and they're sized appropriately for the load in the circuit. Okay, so what that means is if you're going to measure current, I'm just make this up arbitrarily. If you have a 500 amp bus, you probably don't want to use a 500 amp CTs because that doesn't have much headroom unless you know for a fact you're in the middle to the low range. So try to size your CT so the typical current is in the middle of the measurement range of that CT. All right, that's a good rule of thumb. All right, that's an important thing. So, but also check the manufacturer's specifications so all accuracies are appropriate for your application. So when we talked about the accuracy of the energy meters, the power quality meters, CTs and PTs and any of the transducers can be a weak link in that chain. So if I have, like I'll take an example, a Dranitz meter, which may be 0.1% or 0.2% on voltage and current, and I put a 1% or a 2% transducer in front of that, well, that transducer is the weak link in the chain and reduces the accuracy of your voltage and or current measurements, which reduces the accuracy of your power measurements. So just be aware of this in your application to make sure you choose the right transducer for that. All right. Also note that CTs and PTs can act as low pass filters. The bandwidth of these and the cutoff is typically in the 400, 500, 600 hertz range for typical CTs, fixed installed CTs, such as metering CTs and also PTs. That is perfectly fine. That is perfectly fine to measure just your base stuff that you're measuring. But if you're going to look at harmonics, you're going to look at transients, these transducers could be filtering out the very things that you're looking for. Sometimes you may not have a choice. you're not going to connect your instrument in a 13 kV circuit directly, and you may have to deal with a PT. So just be aware that you may not be seeing some of the signals that the instrument's capable of, and keep that in your thought process. Again, you have to connect these safely, so you need to use these PTs and CTs to do so. So just be aware if you're not seeing what you're looking for, they could be filtered out by those things, and plan accordingly. So the moral of the story is the results are only as good as the weakest link in the chain. Make sure that they're appropriate for your application, and a poor selection or choice of these PTs and CTs can reduce your accuracy and bandwidth and otherwise negatively affect your measurements. Okay, and that's it. That's it for module number 1. Chat up any questions that you have. I'm going to change screens here and put up our schedule so you can see what we have coming up in the future here. So please chat up your questions. And Patrick asked, oh no, a response from Stacy to Patrick on his question about the 40 volt delta systems. Okay, so we're going to hang here. Feel free to chat up any other questions that you have. While we're doing that, I'm going to share a different screen here, and I'm going to put up our seminar and our web meeting schedule here so we can all see it. So this is on Dranitz.com. It's on the product training page. This is the same page that you folks registered for this web meeting on. And you can see we've completed our August 5th web meeting. We had very good attendance. Thank you. Today is the August 12th meeting. And next week, as I mentioned before, our next meeting is hosted by Electrotech. And that's going to be an introduction to PQView, what PQView can do for you. PQView and our related software called PQView DE are meant for use with our fixed systems. And we spoke about that last week. So if you're interested in attending that web presentation, click this register here button right over here. Okay, that'll take you to the Electrotech website, which will give you a registration for that. Like you saw with the Dranitz registration, we'll bounce back with an automatic email that tells you the login information. So after that, we have on August 26th, our second of our 5 modules is energy monitoring overview. So what are we measuring? What are the difference between AC and DC? What's the relationship between watts, VA, VARs, power factor? What is demand and energy? Talk about utility billing and some of the factors that go into utility billing. We're also give you a case study on energy efficient lighting. So it's going to kind of pull together that information and look at an LED, a CF bulb, and compare those to a incandescent bulb. You know, are we saving the energy on that? So on September 9th, happy birthday to me, is our 3rd module, which is our power quality monitoring module. So as we evolve through our virtual seminar here, we're going to do an introduction to power quality. We're going to look at what are the appropriate standards for power quality monitoring from the IEEE, the IEC. What standards do you follow? And that's really regional dependent, what part of the world you're in. But we're going to define what a sag or a dip is, a swell, a transient. How do we determine PQ directivity? What are those rules of thumb? And what I mean is, did my power quality event originate on the source or on the load? So we'll give you some rules of thumb to look at that. And we're going to give you a case study of a hurricane. We had a hurricane come through here in Edison. We have a lot of instrumentation. So basically, it summarizes all the things that we spoke about in this particular module. Those sags, those swells, those transient, we got all that type of data during that hurricane. So module number 4 on September 16th, we're going to talk about harmonics. And this is another major part of power quality concerns. We're going to talk about, well, what are harmonics? We'll just break them down. What are the standards? What's the difference between the IEC and the IEEE standards? Which one should you follow? Which is important. That's a regional thing. We'll talk about rules of thumb. What are triplet harmonics and what are some rules of thumb appropriate for that? In addition, we're going to wrap up our case study on energy efficient lighting, where in our energy section in module number 2, we spoke about, you know, are we saving the money in these energy efficient lighting? And in this module, module number 4 for harmonics, are there harmonic concerns using these energy efficient light bulbs? Are there harmonic concerns with an LED or CF bulb? Okay, we're going to compare and contrast those certainly to an incandescent bulb. And the last of our 5 modules is on September 23rd, where we're combining all of this, and we're going to do a seminar on how to do a power survey. So how to pull all this stuff together, how to do a combined survey for energy, for power quality, or both together. We're going to go through step by step the systematic steps you need to go do that from beginning, middle to end. And we'll kind of pull together our prior 4 modules on how to do that. So again, if you want to register, if you haven't done so already, and I know a lot of you have, just click this register now button on that page and we'll get you into that system. So, all right, thank you very much. That's what we had here today. We will stay here and answer your chats. We're happy to do that. So please chat up any questions that you have and we'll monitor them. Thank you very much. We will see you hopefully next week at our Electrotech presentation. So take care. Thanks for your time this morning.